Good afternoon, everybody. I'd like to welcome you all to the second session of AIUI. It's a user modeling session. And I see that most of you made it back on time from lunch. I'd like to invite the first speaker that will present task load estimation and mediation using psychophysiological measures. And the paper will be presented by Rahul Rajan, which is a PhD candidate at Carnegie Mellon University.
Thanks. So hey everybody, my name is Rahul, and this was work done with Ted Selker and Ian Lane at Carnegie Mellon. Okay, so here's a brief overview of the talk. I'm going to discuss the problem space, which is distracted driving. And then I'll go into two experiments. In the first experiment, we're asking if are notifications distracting? And in the second experiment, we want to be able to autonomously mediate these notifications. And then I'll end with the conclusion. Okay, so the problem space. It's a well-researched fact that talking and texting while driving is dangerous. But when they refer to texting here, it's a two-way interaction. And what we were curious about is if it's only a one-way interaction, just notifications, is that going to be distracting as well? As we all know, notifications are becoming more and more prevalent. Everything is trying to send us some notification or the other. So the question we had was, are notifications distracting? And if they are, and actually a second part to that was, does the modality matter? So if I give you visual notifications versus oral notification, does that make a difference? And the second question we had was, if notifications are distracting, then how can we mediate these notifications? Okay, so the first experiment, what we're asking is, are notifications distracting? So I'll quickly run through the experimental design. What we wanted here was a driving task where we can get the workload to change rapidly, because we want to be as close to the real situation as possible. So when you're driving on the highway, for example, you're cruising, it's a low workload. But when you're merging or exiting onto the highway, you're trying to overtake someone else, it's a high workload. So drivers experience this shift from low to high workload and then high workload to low workload. So how do we go about getting that change in workload? So what we ended up using is this thing called the Contratask, which comes with the Open Driving Source Simulator. And I don't know if you can see it, but there's the yellow bar in the screen, which is controlled by the computer, right? So, and the blue cylinder that you see is controlled by the participant using a driving wheel. So the participant's task is to track the yellow cylinder with the driving wheel. And that kind of simulates a curvy road. And we can use the speed of the yellow cylinder to control the driving workload. So this was shown in a paper. And so this is how we achieve this rapidly changing workload. Now the goal is, I'm trying to do this experiment where in the control condition, we're going to be sending notifications randomly. That means in both the high and low workload conditions. But in the test condition, we want to send the notifications only during the low workload. So that brings us to notifications. How do we design these? Right, so that's our secondary task. And one of the things we wanted with notifications was to be able to separate out attending to a notification to responding to it. Right? So you're driving along and you indiscriminately get notifications. So here's an example. Hey, you want to get a drink tonight? Right? And that's separate from responding to it, right? Mostly what we see is drivers when they're at a traffic stoplight or in a traffic jam, that's when they respond to these notifications. So you say, can tonight, how about tomorrow? Right, so how do we design a task that's repeatable, doesn't have learning effects, and distinguishes between attending and responding? So what we ended up using here is something called complex span task, which is popular in psychology for testing working memory. And let me quickly run you through what a complex span task is. So and these can be given orally and visually, so they can be read out or visually presented. So let me give you a quick example of this. So here's a math task which we think represents symbolic notifications. So users presented with this equation, and they're supposed to say whether the equation is true or false, right? So they say true or false, and then they're given a letter which they have to remember. And then another example is a sentence notification. They have to say whether the sentence makes logical sense. So after yelling at the game, I knew I would have a tall voice, which doesn't make sense. It's false. And then they give another letter to remember. And then a third one, another equation. This one's true, and they have to remember F. So after this, they're asked to remember the 3 letters in sequence, right, which is kind of hard. So PQF. So that's a complex span task. And what we said was this part where you get these notifications, that's where you're attending to a notification, that you're just processing this information. And the part where you're recalling the 3 letters, that's where you're responding to this notification. So that way, we were able to distinguish between both. So let me show you the 2 tasks together. Right, so here we have our driving workload, which alternates between high and low. And the participant is given 3 notifications, right? And then we pause the simulator and ask them to repeat the 3 letters that they got during the 3 notifications. Okay, so zoom out and show you an actual run. So an actual experiment run takes about 8 minutes. We have 10 math and 10 sentence notifications that are interspersed during this experiment. And so you can see that a participant gets 3 to 4 notifications, after which the driving is paused and they're asked to respond. Okay, so in this way, we did a study with 20 participants. The control condition was non-mediated, so the notifications are delivered randomly. And in the mediated condition, there's a human who can see the workload the driver is experiencing. So when they notice that the workload is low, that's when they give the notifications. Also, the notifications were delivered via audio using a text-to-speech interface and visually using a Google Glass. So participant did this experiment 4 times. It's within subjects, and the order was counterbalanced, so to counter for learning effects. And what we found was the mediation effect is very significant, right? So there's a big difference in performance when notifications are mediated, and what that tells us is that notifications are distracting. As far as the secondary question goes, the modality effect is not significant, so there's no difference really if the notifications were delivered orally or visually. Okay, so while the participants were doing these experiments, we had also strapped them up with a number of sensors, which is on the website, and which is on a link in the paper, all the data. So all of these signals have been shown in some paper or the other to be useful for recognizing affect and cognitive load. So what we did is we analyzed 5 signals which we thought might be the most promising: instantaneous heart rate, pulse transit time, skin temperature difference, electrodermal activity, which is galvanic skin response, and pupil dilation. And what we're trying to do here is trying to use these signals to figure out when a user is both attending to a notification and driving. So if you can see on the graph, it's the blue bars, where a user is engaged in both the primary and the secondary task, right? So that the idea is that when they're multitasking, that's when they're cognitively loaded. And we're trying to see if we can use these signals to figure out when a user is multitasking. And what we found out was, we only got success with the pupil dilation measures. So what we're doing is taking overlapping windows, extracting statistical features, and trying to learn a random forest classifier model for each of these signals. And we found that with the pupil measure, we were getting an AUC-ROC of 0.85. With the other signals, we were not doing much better than random. Okay, so that takes us to the second experiment. So we built a model, right? So now the obvious question is, okay, can we use this model to mediate when notifications are sent to the sent to the user, right? So now we know, hey, there's a user in a high load. Maybe we should delay this notification to them. So can we do that? All right. So let me run you through the experiment design again. We use the same contra task here, but for the secondary task, because notifications are what we want to mediate in the first place. So here we have a gear changing task where a number from 1 to 6 is presented to the user, and they have to change to the right corresponding gear. And then we have the mediation task, which in this case we only use the oral notifications. Okay, so let me show you all of them together. So here we have the alternating high and low workload that the driver is experiencing. And notice that during the high workload, they also have the gear changing task. So we're trying to load them. And then in the control conditions, we're going to give them notifications randomly. So they're going to get notifications in both the high and low workload. And the goal is, using the model we have from the previous experiment, be able to mediate these notifications. So we want, whenever the user is in a high load, we want to be able to delay the notifications till they're in a low workload. Okay, so how are we going to do this? Again, we're going to use pupil dilation measures. We use this headset from Pupil Labs. You can 3D print, they have the 3D print models, and they just use a $50 webcam, so it's really cheap, and the software is open source. So you get the pupil dilation signals, right? And what we do is we take a 5-second window, and then we shift that 5-second window every second. So every second, that window is being shifted. And from every 5-second window, we're extracting statistical features and pushing it through the random forest classifier that we trained in the previous experiment. So at this point, every second, we're getting a classification that says the user is in a high load or a low load. And if you respond every second, it's going to be too sensitive, so we need some sort of smoothing. From the pilot experiments, what we found was if we use a simple smoothing mechanism, which is if we see 2 continuous highs, that indicates the user is in a high load, or if you see a high, a low, and then a high again, that means the user is in a high load. And then we want to resume the notification only if we see 5 continuous lows. Right, so now we're sure that the user is in a low working load. So that's when we want to resume the notification. So I'll play a demo of an experiment. This is an actual experiment. On the top, where we have the driving workload, that's the ground truth. That's the load that the user is under. And below that, the pupil classifier is the output from the classifier. Right, so it's telling us whether it's low or high. And on the right, you can see the pupil and the contra task. I'm not sure if the audio works, but you should hear the notifications being delivered to the participant. And if the system detects that the user is in a high load, it's going to pause the notification. So, but what you really want to track here is the classifier able to track the ground truth? And you're going to notice like a 2-3 second delay. That's because we're using a 5-second window. Okay. So we did an experiment where we had 10 participants come in. It was within subject. So they're doing this experiment twice. Once it's mediated, once it's non-mediated, and the order is random. So was the mediating agent successful? So to answer this question, we looked at the participants' performance and the agent's performance. So we found a significant difference in the gear changing task, so people were able to more quickly change to the right gear, but not in the primary driving task. And with regards to the agent performance, we found, this is post-analysis, so if you use an HH or HLH pattern, we found an accuracy of 63%, but if we analyzed a number of other patterns, so for example, if we had waited for 3 highs in a row, we would have got an accuracy of 71%. So this can be further explored using HMMs or something. So here's the conclusion. The problem space was notifications while driving, and the question was, are these distracting? And if they are distracting, can we mediate them? We did the first experiment to answer the first question: are notifications distracting? And we found that they are indeed distracting, and it's regardless of modality. So if you use audio or visual, they're going to be distracting. At the same time, we were also collecting data so as to build models, and we had success with using pupil dilations. So then we used this pupil dilation model and asked if we can autonomously mediate notifications now. And so we demonstrated this real-time autonomous mediation. We showed improvement in user performance, and we also analyzed the agent's performance. So I'll take any questions.
Thank our speaker. And we'll take a few questions.
So I guess my question regards the definition of distracting. So you found from the first experiment that you could see an effect on pupil dilation, but not on any of the other sensors that you tried. So those sensors are also known to be perceiving emotional arousal.
Yeah.
So apparently there was no effect on the emotional state of the user from the notifications, right? So there was a change in pupil dilation,
right.
So cognitive load,
yeah.
But that didn't impact the affective state. So in a sense, you could argue, well, maybe they were not distracting because users were not, say, getting frustrated or getting in some sort of a negative affect
right.
because of the notification. So increased cognitive load makes sense because
right.
they do have to attend
right.
to notifications.
Yeah.
But in the end, if they don't have any other negative side effects,
right.
maybe they're not distracting, they're just being perceived and processed. Do you have
a so I think with affect tracks a lot slower. So here we're giving them distractions every 4 to 8 seconds, and so pupil responds a lot faster to that kind of load. So you can see the pupil dilation changing much quicker. Whereas with affect, so they might have been stressed for the whole experiment, which is only 6-7 minutes long, right? So you might have seen a gradual change in their heart rate becoming faster, or them being tense during the whole time, but it doesn't track as fast.
Since there is no other question, electrodermal activity tracks spikes in emotional arousal, and they are instantaneous.
Yeah.
So in theory, if there is a change in your emotional valence,
yeah.
you should track it, right?
Yeah.
Yeah.
Okay, I think that time is up, so let's us thank our speaker again and further questions during the break. Our second speaker will present the paper titled What Belongs Together Comes Together. It talks about activity-centric document clustering for information work. And the presenter is Alexander Selinger, which is a PhD student from the Technical University of Darmstadt in Germany, works all telecooperation lab under the personal assistance system area and working on analysis of business process to provide better assistance for improvement. So please.
Thank you for the introduction. My name is Alex, and I'm going to present this paper here with that I've written with Benedikt Schmidt, Immanuel Schweitzer, and Max Mühlhäuser. And the goal of this paper was all about helping information workers to organize their information. So, and it tends to be the problem that information work is a challenging work type because because of multitasking, information appears, and information workers really have to deal with this. So there are, of course, frequent interruptions, and the increase of information is not stopping. With more and more devices like smartphones, tablets, and notebooks, and even all of these new apps that we're all having on our devices are producing information that we have to organize in some way. So this work was all about trying to really get all this information and trying to cluster the related information together into groups that help the information worker better getting organized. So there's of course some related work here. We have some activity-centric task management approaches like Grouper or Task Tracer that try to help the information worker doing their information work by showing or trying to show the user what information is somehow related to each other. However, these tools are really much more manual work, so the user or the information worker really has to maintain this information by themselves. So there are also some automatic approaches like Task Predictor or CAID, which try really to get the information from interaction history to identify which activity, so what activity the user is currently working on, and then try to organize this information. So there's also the other topic of content-centric document clusters. So they are working really on the content of the documents, trying to find relations there. For example, a really very easy way is the TF-IDF metric that just uses the occurrences of words and try to cluster this together. Another approach is, for example, the latent Dirichlet allocation, which is more of a high-level clustering that takes the topic distribution of all over the document. So, however, there's the problem that none of this work really focus on both sides. So we have some activity-based metrics and we have some content-based metrics, and this work really tries to combine both of these metrics together. So to achieve this, we introduced a document relatedness metric, which is pretty easy. It takes two documents and returns a value between 0 and 1, which means high values determine that the two documents are not really related to each other, and on the other side, they are really high related to each other. So as you can see down on the table, we have collected from related work. We have 3 activity-based approaches using the applications or the use of applications. Here also some most used together documents are probably related to each other, or if documents are worked in parallel, are also related to each other. So then, of course, as I told, the content-based metrics also work very well here. So, and now you might ask, well, we could simply average all these values and have a solution for combining these both worlds together. However, this is not the ideal solution because some metrics may be better than others, and so we have to really deal with this. So to solve this problem here, we're just introducing a weighting factor that allows you to change the amount of influence of all of these metrics, and then you can give the metrics that are working better more influence than the others. However, there's also another problem because all of these metrics may not contribute to the contribution of these metrics are made different. So the average contribution of all of these metrics may be higher or lower, and we have to correct these values as well. So by just using the average value and divide it by that. So, so how do we find out these weighting factors? Because you could, of course, say that you have a fixed value set that you use and apply for each user, but we would like to have an individual solution for each one of us. So we converted this problem into an optimization problem where we define a function that calculates how the automatic generated clusters are compared to the optimal structure. So, and you might now ask how to get this ideal solution. Well, we use some cluster. We propose that we are using some small part of the. Sorry, I'm starting again. So this function returns if the optimal structure is equal to the structure that we're automatically generating. And we let the user manually cluster a small part of its document corpus to just get these values here. And then we're using an optimization algorithm that calculates us the weighting factors. So in our paper, we are using the particle swarm optimization, which tries to which tries to find an optimum by improving the candidates, by iteratively improving the candidate solution. And this is pretty much a genetic algorithm which is inspired by bird flocking, where each bird has to maintain its distance to each other. So, and of course, if you would like to have something for a cluster, then you of course have to use a clustering algorithm, and we are using the bottom-up clustering here. So just to get an overview again about all of this system here, so we're splitting the approach into a training phase where the user has to manually cluster some of its documents, and then we're trying to figure out how these weighting factors have to look like for each individual user by applying our particle swarm optimization approach here. So, and then we can use these weighting factors in the second step and apply and cluster the rest of the corpus with these values here. And then we have a semi-automatic approach that can cluster all of the rest of the documents here. So to evaluate our system, we have conducted a user study with 8 participants, and we are having tracked our users using the CrakeMe desktop platform, which was also developed by our lab. And these participants had to manually cluster all of their documents to get to get a gold standard where we can check and evaluate against this our approach. So as you can see on the lower right, this is the evaluation user interface that was shown to the user, where the user had to manually cluster their documents and put them into the right group here. In our study, we had over a couple of weeks where the user was automatically tracked, and we collected over 28,000 data items in total with about 8,000 unique documents and 50,000 document accesses. So we're sure that this study was not performed on a small test set, but on a more larger one, so that we can really see the system work, or if it works or not. So just to get an overview about this CrakeMe platform, it's a multi-device platform that can track the mobile space, the desktop, and the social space. However, on this work, we're just using the desktop version. And it could also collect multiple sensors, such as physical sensors from the mobile phone, But in this case, we're just using the virtual sensors, such as the document usage, the app usage, and of course the document content, so to get both the activity-based approaches and the content-based approaches here. So it's all of an automatic tracking solution, and we have used this to track the user and to analyze our, and to evaluate our system by implementing our approach into the system itself. So let's see how we're performing. So the first evaluation was just made using a single metric. So this is the traditional way that all other work is using. So we're evaluating against the full data set, and we compared the manual cluster set with the automatic generated one using the adjusted mutual information or the adjusted rand index. And as you can see on the slide, the content-based approaches really outperform the activity-based approaches here, with TF-IDF leading here in our study. Just a quick information, so higher values are better and low values are worse, of course. So in the second step, we're applying our hybrid feature set approach by mixing up the content-based metrics and the activity-based metrics. And we can see that we're definitely getting higher values here for the adjusted mutual information and/or the adjusted rand index, which means that the mix using content-based information and activity-based metrics are performing really well. Interestingly is that if you're just mixing up activity metrics or content metrics, you're also getting lower values, which we did not expect. We expected that even if we are mixing up more activity metrics together or more content metrics together, we would get higher values here as well. So how does these contribution, or how does these single weighting factors look like? And as you can see on the left side, this is the mix using content and activity metrics. We can see that they are pretty much average, and a little bit more activity metrics contribute to the overall results here. As you can see that we have app context, the time-related 1 and 2 metrics are a little bit over half of the contribution of this result. So to conclude up and to summarize up, the comparison, we showed the comparison of activity and content metrics over a larger data set. We've seen that the hybrid feature set really outperforms the single-based metrics with 0.37 against 0.5 using our hybrid feature set approach. We've seen that we can create a net self-adaptive system, which means that we're not just using a single fixed value set that works for everyone, but we have developed a system that provides a method to calculate the weighting factors for each one of us. So it really adapts good for different document domains here. So as a future work, we definitely have to look in overlapping clusters, because it's usually not the case that you can put a document into exactly one cluster or in one group. Even the file system has more structure here. We have a hierarchical structure where we can put more documents in multiple clusters here. And we have to really focus how does these clusters really represent in the user interface at the last step here. And that's also a very big point here, because we are not having yet a full working system for the user. From the user's perspective, we would like to have some interactive system where you can really work with and where you can also correct errors that the system made, and to provide a better solution for future clustering here. So I'm finished and open for some questions.
Let us thank our speaker. And there is room for a few questions. So, is there anybody that is interested in asking? Okay, until he gets to the microphone, I'll touch upon the last sentences of you. What can you think about the practical implications of your study? What can a user do tomorrow morning, assuming that your system works? How it will help us?
Yeah, well, we have a system where the large amount of data is more put into structures. So we have some groups that, some information groups that only focus on some specific topic where we can make the user more concentrate on a single task instead of looking all over the place and have to maintain the whole corpus that he's collecting. So we're more of a kind of having less work for the information worker to do manually.
So helping me find out what I need for the current task, making it readily available for me?
Sorry.
For making all the documents that I may need for the current task available instead of me searching for them? Okay, we'll take it offline. Okay.
Hi, Steven from Minnesota. So we got this one question is, have you looked at how much training data you need from one user? Like how does the accuracy improve over time? Do you have the rough idea?
Well, for the study we used, I think it was half of the data that the user had to actually, that we're taking into context that as a training data. So we have split the data into two parts. We haven't really looked into the data and made a decision where we put where we split the data, but I can imagine that if you're running it in a longer time space, then you can of course have something that's solving this cold start problem here, where we just have to cluster, I think 10% or so, but I'm not sure because we have not looking into that.
Yeah, I mean, I guess I'm just interested because you want to not let user do a lot of effort, but just, you know, trying to make it as accurate with least effort from user, right? So,
Yep.
Yeah, thank you.
Okay, any more questions? So let us thank our speaker again. Our next paper will be Interactive Intent Modeling for Multiple Feedback Domains. And the paper will be presented by Pradram Dai, which is a PhD student at the Helsinki Institute for Information Technology.
So, hello everyone, thanks for introducing me. So my name is Pedram and I will present our paper, Interactive Intent Modeling from Multiple Feedback Domains. Generally we are dealing with the interactive system and we want to use user feedback, different types of user feedback in that human-computer interactions to learn the hidden intent of the user and by it to improve the performance of the system. So, the search scenario that we are talking about is called exploratory search. To define exploratory search, first let's look at the standard lookup search. So we have a user. The user has some kind of a item in her mind that wants to find, and she used a search engine, any kind of search engine. For example, here Google, by forming a query, and then the search engine gives the results to the user, and that's it. But there's another family of search scenarios called exploratory search, where the user is not completely sure what she's looking for. So the user doesn't know what she wants, but she can start a search by a query and then see the results and then change the query and do interaction with the system until she finds the intended items. It's interesting to know that up to 50% of searching in general is informational, where the user wants to learn something from the system. Usually the characteristics of this exploratory search scenario are that the user doesn't know what she wants, the target item that the user is looking for is usually complicated, complex, like the user is looking for a paper or something, which is hard to describe by just a query. And the user just have some abstract ideas about what she wants. For example, the user is looking for a reinforcement learning paper about a particular application, but the user only knows that I will start with the query reinforcement learning. So the key idea in this kind of search scenarios is that the user has to explore the information space in order to find the intended items. As you can see, the search scenario itself is quite vague, so it's a little bit hard to define it in a mathematical formulation. Let's go to the next slide. Okay, so we consider the case that the user is looking for a document. The simplest case is when a user wants to do a literature survey about a topic. So there's a set of documents denoted by D, and a set of keywords that describe those documents denoted by K. We make some simplifying assumptions about the user behavior. So the basic assumption is that the user is looking for relevant documents. And the user starts with a very abstract understanding about her needs. So we represent this abstract understanding by a set of relevance distributions. So for example, here, the user is not sure whether document D1 is how much relevant, but there's a distribution on the relevancy of this document that models the uncertainty of the user about the relevance. We call this set of distribution user intent, and we can denote the expected relevance of each document and each keyword by ED and EK. So the general goal is it's just an optimization problem. We want to find the document that has the highest expected relevance in the user mind. The challenge with this optimization problem is that the function that we want to optimize is in the user's head. So we cannot see the function, and we cannot sample the function because the sampling is quite expensive. We have to show one document to the user and see the feedback of the user about that item. So this kind of black box optimization problems where the objective function is unknown and expensive to sample has been discussed in different literatures like multi-arm bandits and Bayesian optimizations. So just by sampling user feedbacks, we want to solve the maximization problem. Generally, to solve this kind of problems, we have to handle exploration-exploitation dilemma. So at one point, we have to show different documents to the user in order to see if they are relevant in user intent or not. But on the other side, since we can only ask limited number of times this kind of questions from the user, we have to try to show documents that we guess are more important to the user more. And we assume that we can ask, and documents or keywords, we can ask about the relevance of documents and keywords from the user. So in order to solve this maximization, I cannot go through the details of our solution because the time is quite limited. So just the nutshell of ideas that we used. First, since the user can give two different types of feedback on documents and keywords, first, based on some mathematical assumptions, we define a feature transformation in order to move these documents and keywords in a same feature space. After doing this, we propose a probabilistic user model that connects these feedbacks in a unified form, and then we use Thompson sampling on the probabilistic user model to solve the exploration-exploitation dilemma. So we have a user model based on user feedback on documents and keywords, and we use this probabilistic model along with Thompson sampling to solve the exploration-exploitation dilemma. Let's just skip that. Okay, to evaluate our method, we performed simulation study and a preliminary user study. In the simulation study, we wanted to see if we consider these two, we wanted to see how much the performance of the system changed when we consider both types of feedbacks in the search engine. So there's a simulated user. At each iteration, we show 5 documents and 5 keywords to the simulated user, and this simulated user can provide feedback to them. And the results show that if we consider both types of feedback, the performance improves compared to when we just show one type of feedback to the user. We also performed a preliminary user study on 10 university students. We implemented the algorithm on a search engine called Cynet. So Cynet is an exploratory search engine. On the left side, there's a radar interface where the user can give feedback to keywords by dragging them toward the center or far away from that. On the right side, the user can see the list of documents and their abstracts. So the Cynet system uses an algorithm, a multi-bandit algorithm called LINREL. And in our user study, we didn't change the user interface. We just replaced LINREL with the new algorithm called coupled multi-arm bandits. And the initial results based on questionnaires and just the percentage of relevant documents shows that there have been some improvements, but the differences are not significant. Yeah. But yeah, this was just a preliminary user study. So in summary, we introduced an algorithm called coupled multi-arm bandits. And the idea was that it solved the multi-arm bandit problem, but when we have different types of feedbacks. And one motivation behind this project was that there's a MINDSEE project, it's an EU project, that tries to do the information retrieval by using brain signal and physiological signals. And in that study, we noticed that some of these relevant signals are only available for documents and not the keywords. So that's our future work, to integrate the system with brain-computer interaction kind of systems. Thank you.
Let us thank our speaker. And there is a room for a couple of questions. Are there any? Okay, so I've got one for you. You were comparing a couple of algorithms. I was wondering about what was the baseline, because maybe I missed that, but what was the baseline for your comparison? Because comparing the algorithms is one thing, and having some kind of a reference is something that may provide some better understanding.
Of course. So for the user study, we compared the algorithm with LINREL algorithm, which is a baseline in the contextual multi-arm bandit literature. And also the Cynet paper compared itself with other algorithms too. So we just compared our system with the basic Cynet system. So we didn't directly implement all the other methods. And in the simulation, we can just say that we compared with random recommender and some kind of a biased recommenders, but nothing more. Yeah.
Okay, thank you. Any other questions? So let us thank our speaker again.
Thank you.
The next paper will be inferring a player's need for cognition from hints. And it will be presented by Javed Khan, an assistant professor at the Industrial Design Department in Eindhoven University of Technology. Javed Khan was working on, during his PhD, on context-aware computing and with application on the family of communication system and the same department, and have worked in the past in Philips research. Vodafone and both in the Netherlands.
Thank you for the introduction. My co-authors are Carlos Santos and Panos Markopoulos, and this work is done also in collaboration with NHTV, Breda University of Applied Sciences, also in the Netherlands. So the motivation of this work is whether we can use in-game behavior to detect players' stable personality traits that would be useful for adapting then games and systems beyond games. So first I would like to define for you need for cognition. Then I'm gonna shortly discuss the game that we designed for this study, which we called it Nanobots, highlight the method and results. So need for cognition is a stable trait that indicates how much a person is willing to engage in cognitive activities rather than apply mental shortcuts and heuristics. And essentially, it's a questionnaire, and there is a score that you get, and it dichotomizes people in two categories, those with high need for cognition, who are essentially inclined to mental problem solving and assess situations with higher degree of elaboration. And those with low need for cognition who are prone to less elaboration and follow more heuristic and empirical strategies. It's measured in a scale, and it has been also applied in advertising, in other persuasive technologies. So we set out to design a game that would allow differences between people with high and low need for cognition to manifest naturally during gameplay. This is where game environments excel, offering ample opportunities to exhibit choice behavior within a controlled environment, and where it is straightforward to record player actions. So we developed this game, which we called Nanobots. You can see the link where you can actually experience the game yourself. It's a simple two-player turn-based game, and essentially players control the movement of a set of units. And the objective is to eliminate the units of the opposing team. Within the game, we included the need for cognition questionnaire, so you see that on your right-hand side. So just to give you an idea of, just to sample an item. So the second one is, I really enjoy a task that involves coming up with new solutions to problems. And we also included hints in the game itself. The hints could be either requested explicitly by the player, or they would appear after a few seconds. We logged several things while our participants played the game. So the number of hints requested, the number of hints actually followed, the number of turns that players took, the total duration of gameplay, and their score. So essentially, our research question was, does behavior around the hint mechanic correlate with the need for cognition? And more specifically, we would hypothesize that there is a negative correlation between need for cognition and a hint mechanic. So just to highlight the main significant result we found. So we see a significant negative correlation between need for cognition and the number of hints followed. So we had a data set taken by 105 players. And there, in this figure, it's important to highlight that we didn't account for the first two games. So we only averaged the followed hints. This is what you see in the different game rounds from so gameplay 3 to 6. We also, well, one could hypothesize, since this is a strategy game, it might biasing for people who are high on need for cognition. So we did check all other variables that we logged, and we see that it's actually not biasing, it's not favoring players with high need for cognition. So as a summary, we showed that a generic game mechanic can be utilized for inferring stable personality traits. And supports the, moreover, we showed that within a game following, logging the followed hints, it could support the unobtrusive detection of need for cognition. So we would need for participants to actually fill out the questionnaire to detect that. Now, possible potential and possible adaptations for games, it would be, for example, for high need for cognition players, to include additional cognitive tasks within a level before they move to a next level. Or, for example, for content purchases, so another part of a game, they would, for example, require in-depth information, whereas low need for cognition players would probably need more visual complex stimuli for content purchase again. Or, for example, another example would be for low need for cognition players in explorations games to get an influential figure to impact their engagement and exploration within the game. Obviously, these are just suggestions and would need to be checked in future work. And with that, I would like to thank you for your attention, and if there are any questions.
Well, let us thank our speaker.
So I was actually pleased to see that you studied need for recognition, because I think it's one of the user traits that has been underlooked in our community. But I was wondering, so the hints could be either requested, or you said they would be provided by the game, right?
Yes.
So did you check if there was a difference in how people with high or low need for recognition requested hints?
Yes.
And also in your hint followed, you didn't make a distinction between whether the hint followed were related to hint requested or hint provided by the system.
Yes.
Because there could be a different, so I was wondering if you could comment
Yes,
on
indeed. Well, we highlight that in the paper, and indeed we looked at the requested also hints, the number of requested hints, although it was in that direction that the hypothesis assumes, it was not statistically significant. So that's something that indeed we need to check and make that difference in the followed hints and requested hints. So although it was in the direction that we expected, it was not statistically significant.
But what was the direction? What was it?
So yeah, again, the low need for cognition people requested more hints. So it was towards that direction, but not statistically significant.
Then I have another question. So one of the interventions for low need for cognition users that you're suggesting is more visually complex stimuli. How did you come up with the connection between more complex visual stimuli and low need for cognition?
Yeah, this links to the definition, and yeah, they would tend to follow more heuristics, and they would it appeals to them more visual stimuli rather than textual descriptions. So that's something that we saw from literature, from prior literature.
But complex, would that fit the bill? Because maybe complex requires too much cognition.
Yeah, that's a good point. And
Too complex,
yeah.
visual, yeah.
I would need to think about that. That's a good point. Yeah. Thank you.
Hi, I really like the paper. I also like the idea that you have here at the top of your last slide, but I'm afraid you're there overstating a little bit, because you're saying you can use generic game mechanic to infer stable personality traits. And if you look at your main result, you had an R of like 0.3 or something, right? So that means an R square of about 0.1, which means you're explaining 10% of the variability in that personality trait. So I would be a little careful in saying something like you can infer a personality trait from this data, because you're 10% of the way there, which compared to some of the machine learning people here, 10% would be kind of a pretty bad AUC, right? So it's definitely a step in the right direction, but I would be very careful with the word infer.
Thank you for that point. Yeah, indeed. Well, as it was mentioned by the previous question, I think this has been overlooked in the community. So it is a fair study, and yeah, thank you for that suggestion.
I'm curious to see what you come up with next to make it even better. Yeah.
Thank you. Thank you for the suggestion.
So one thing that comes to my mind, first of all, good paper. It's very interesting. The thing is, one confounding factor could be their experience with games. Like, how much have they played games before, and are they that sort of mentality that they always want to win before, without any hints? I think that could be very...
Yeah, a good point. Yeah, I forgot to mention that our participants were the students from the Academy for Digital Entertainment who are trained to become game designers. So, yeah, we would assume that, they have game affinity, and we would assume that the variance is not that...
But probably
much,
most of them wouldn't want to have hints.
Sorry?
If they're game designers.
Well, they were players for this particular study, and I don't know if you're a player yourself, but I think when you're playing, maybe you would reflect afterwards as a game designer what this game means for you, but not while you're playing. I think so.
Thanks.
Yeah.
Okay, let's just thank our speaker again. The next paper will be driver classification based on driving behaviors. And the paper will be presented by Cheng Zhang, which is a PhD student in the computer science department at Georgia Tech.
right. So I'm Cho. I'm a computer science PhD student from Georgia Tech. So this is my internship project in Yahoo Labs, which is about recognize the driver based on their driving behaviors. So I know everyone's like tired in the middle of the day, and so I will start my talk with a question. So how many of you are driving to work every day? So hands up. All right. So guess how many hours you need to spend on driving per day? So based on the study have done by Harvard in 2007, average like American adult will spend 1 hour and 41 minutes on driving. So that's a lot of time. So what do you do when you drive? So you have personal entertainment, and you are probably some people will text, which is not a good thing to do. And so what if your car and your phone know who is driving or know you are driving? So it can provide you better personalized entertainment experience and give you more safety, like switching the user interface on your phone to the hands-free mode. So knowing the driver can give you better experience and safety in the car. But so nowadays, most cars have those kind of connection, which know which phone is in the car. And why not just like recognize the driver by looking at which phone is connected? The question is, the person sitting in the car can be either a passenger or a driver. So the challenge here is, how can we recognize the driver? The good news here is nowadays we already have the phone as a sensing platform deployed, so which have a rich set of sensors like gyroscope, accelerometer, and GPS. And we also have the car sensor available on all the car produced in the United States after 1996 through a protocol called the onboard diagnostic, which you can get the car sensor like engine RPM and the torque sensors. So prior research have already done used like phone as a sensing platform to detect the driving behaviors. Some work have done like recognize drivers, but they're using customized hardware, or they recognize smaller set of drivers, like 2 drivers. So our work is actually using the smartphone and the car sensor, which is a practical sensing platform to recognize the drivers. The first step we do is we collect data. We have 2 experiments. The first experiment, we collect data in a controlled environment. In the second experiment, we collect data in a naturalistic environment. In the first experiment, we have 14 drivers or participants, which will drive 3 cars in random order and in predefined route. The predefined route was carefully chosen, which have both local roads and highway roads. And that predefined route was around 7 miles. In average, each participant drive 20 minutes per car per road. And in total, each participant will drive 21 miles, like across 3 cars. In the second experiment, we recruit 3 couples who drove like 4 days, and each couple drove at more than 4 hours in the 4 days, and each driver drove at least 1 hour and 15 minutes. After we get data, so we process data. The first step we did was to choose which sensor we're going to use. The phone sensor data logs like gyroscope or accelerometer in a 60 hertz sample rate, but the car sensor data actually have pretty low sample rate. It was 1 to 2 hertz, which holds the sensor which is more relevant to how you drive, not all the environment. For example, we also log the air pressure sensor, but it's not relevant to your driving behavior. So we chose the sensor based on which is more relevant to your driving. We apply a pretty standard machine learning pipeline by first pre-processing data, and then divide time series data into 450 seconds window, which will be used to recognize the driver. And we then divide that window into 15-30 seconds small window, and then apply a majority vote on a supported vector machine. And for each 30-second window, we extract features. The feature we extract here is actually mostly statistical features, and other features like substrum was suggested by previous work. And at the beginning, we have over 6,000 features, and when we rank them based on the info game, we further reduce the features from 6,000 features to around 1,000 features. And after we done all the things, we evaluate the system by applying using method of leave one out. And in the first experiment, we can recognize 14 drivers in the control environment. With the highest result we get is the phone sensor, we can 79% accuracy. But also using the car sensor data, the result was not that good at 30% accuracy, but it's still higher than randomly chance. And by using both phone sensor and the car sensor, we get accuracy around 77% accuracy. So you may already notice there are 2% drop when you have more sensor data. So we think through that problem, we suspect the reason was the car sensor data have pretty low sample rate. Recall that part? It's 1 to 2 hertz. So it have some, it's hard to predict more sensor data, more drivers. And interestingly, in the second experiment, when you only have 2 drivers, and those car sensor data actually did a pretty good job on reckoned driver with an accuracy of 85%. So that's very interesting. And then we did a third experiment by increasing the number of drivers in the first data set. So we start driver number as 2 with accuracy all at 100%. And you can see the blue line is the car sensor data. And when the number of drivers increase, the general trend is drop down until around 30% accuracy. So that's the same result we find on experiment 1 and the experiment 2. And we were also wondering which sensor is most helpful on recognizing drivers. So we rank out the sensor information based on their info gain. We find out the gyroscope and the torque sensor as the most informative sensors across all of them. And so this probably, we guess, probably record because the torque sensor is more relevant to how you drive, how you hit the things. So that's our thought. So in the future, what we're going to do is to first, we'll deploy the system in real time and see how it works and build applications based on that. And we can also improve the classification accuracy by applying other advanced machine learning technology and signal processing technology. So in summary, we present a driver classification mode, which can recognize 14 drivers in a controlled environment with accuracy of around 80%, and recognize 2 drivers in a naturalistic environment with accuracy of 85%. Okay, I'm done. I'm happy to take any question. Thank you.
Let's thank our speaker. And you're already ready with question. Okay.
Hi.
Hi.
Very nice work. Actually, very interesting.
Thank you.
My question is, you mentioned that the gyroscope is actually one of the most informative features.
Yes.
And is there any intuition about that? Because from gyroscope, I can hardly tell anything except the rate of turning or something.
Yeah, so gyroscope, so I've been working with phone sensor a lot. So based on my experience, the gyroscope is more sensitive compared with accelerometer because we also log the accelerometer data. So gyroscope, because we make it a lot more sensitive.
Oh,
sensitive compared with the accelerometer, which are also available on the phone. And the gyroscope actually think about this angle change. And when you do a lot of turns, we guess that will help you. And another thing we also mentioned is, I didn't mention the details, is actually we don't look into one axis of data. We instead add the square of 3 axes together to avoid any bias. That's maybe another reason why it's.
Right.
Yeah.
A follow-up question is, did you use any temporal information on the gyroscope, or you just simply divide them into a lot of windows and concatenate them as a vector?
That's a good point. So we don't use time, we just dividing different windows, treat them separately. But that's sort of thing we can do in the future, apply a hidden mark model, those things to further improve the results.
Yeah, I think that will be useful.
Yeah.
Thanks.
Thank you.
Okay, so I guess it's time to change. So let's just thank our speaker again. And the last paper of this session will be the TIIS paper, and it will be presented by Meshaya Cedric Ovenke. He's a PhD researcher at the Free University of Bristol, focusing on multimodal analysis of emotions, and he will be presenting the work on behalf of the authors that were unable to attend. And the paper that will be presented is Adaptive Real-Time Emotion Recognition from Body Movements.
Okay. Okay, good afternoon, everybody. So, thanks, Mr. Chairman, for the nice introduction. So, my name is Meshai Cedric Overnekem, and I'm here to present the work of my colleague, Wei Wang. So, the work is about adaptive real-time emotion recognition from body movements. Okay, I'll go straight to the point. So first of all, in the context of this conference, the question is, why should we care about emotions in the first place? Well, we start actually from the hypothesis that emotion, expression, and perception is a very important component of natural, let's say, interaction among humans. And then, based on this hypothesis, we, of course, start from the conjecture that we should do the same from human-robot or human-machine interaction. And the main motivations are actually to better understand human behavior during automatic perception of interaction, and also to create more natural HMI interfaces, which is very important for various applications, such as we have heard during the day. So, okay, now first a brief, let's say, a conceptual scheme of what we understand by emotions. So I try to explain it in a very holistic way by splitting actually all the notions from psychology and related fields into two dual ways of defining emotions. On the left side, we have, let's say, the unconscious neurophysiological concept of emotion, which is more like a state related to two dimensions, a dimension called valence, going from unpleasure to pleasure, and then another dimension called activation. This is, roughly speaking, how we could define emotion from a neurophysiological point of view. And then you have, in a dual, let's say, point of view, you have the more conscious and psychological, let's say, definition of affect, which we call feelings. And feelings is, let's say, we can consider it as a conscious access to the unconscious affect. This is actually how we see it. And when those feelings are sustained over time, related to some external stimuli, which is interesting for interaction, then we call them emotions. We just assign some words such as happy, sad, or whatever to some internal states. Now, how are they expressed? Among the many modalities of emotion expression, you have facial expression, you have vocal expressions, you have in a certain extent also some physiological, let's say, expressions, and also postures and gestures, more generally body movements, which is actually the subject of interest of this work. So actually the technical problem we addressed is the inverse problem, meaning we want to infer the emotional state from the observed body movements. I will not go into the technical details. For the ones who are interested, you can look to the paper. I will just give the two major steps we have addressed. The first step is the representation of the body itself. When I mean representation, is really a mathematical representation suitable for a data-driven approach for solving the task of emotion recognition. What we actually did is starting from a general definition of the body skeleton, which you can acquire these days in a very cheap way with 3D cameras. And we collect such skeletons in some short sequences of, let's say, 30 seconds to 2 minutes. And such a skeleton is then transformed into 3 steps approach. In the first step, we derive the kinematic features based on angles, distances between certain joints, and so on. And then we compute some statistical cues of those derived kinematic features. And in the third step, we aggregate those statistical cues to have a global description of the short sequences we extract. And this is done continuously while acquiring data. And then the second step, which is actually the most important step, is to use this representation in order to infer the emotional state. Remember, this was the goal. And the work that has been done by my colleague there is to derive, to modify an online adaptive random forest. So basically speaking, it's an ensemble of classifier decision trees, as they are called. And the modification has been made in such a way that during the acquisition, you predict and you adapt your model in order to improve future prediction and stay consistent with the previous ones. So this is actually the main contribution of the work. And we have evaluated and trained it on some benchmark data sets called the Euclid data set, where there are 4 emotions annotated and 183 sequences. And we basically trained our model only on the apex frames, which are the frames where the body postures are the most expressive. And we evaluated the 3 type of features that we have computed with respect to the baseline results. So, okay, there is an outperformance there, but this was not the goal, as you might have. The goal is always to outperform, but not the final goal. The final goal is to adapt in a real-world setup. And with a database, you don't know if it really works. So what we did is to use this trained model on the Euclid database and ran it on just a real-world scenario, which I will show in a 30-second video. Thank you, Chairman, for reminding me. And voila, so I will just show you and explain what happens during a video. So the person there is the first author, Wei Wang. He's just performing some body movements that the computer is randomly assigning him to do. And there on the left top, you see how the recognition is performing. So this is based on the model that has been trained on the Euclid database, but which is continuously adapting and predicting. Wow. So this is pretty much the essence of the work. And recently we have also, let's say, extended it to going from the basic emotions, which are more linguistic constructs than anything else, to the core affects, which I explained in the very beginning, which is the more principled way of representing emotion. And here, just a few seconds video, you can see how the valence is predicted in time. And this scenario was a child-robot interaction setup, where the child is being captured with the Kinect camera, and we continuously predict the valence arousal values and adapt the model. Okay, voilà. So the conclusions are the following. So we have been able to design a real-time emotion recognition system from body movements. One of the key features of this system is the online adaptation to streaming data. And we have recently extended it to dimensional effect to have a more principled representation of emotion. And more importantly, we have shown that it can be implemented in real-world scenarios and where the performance is more than reasonable. And that's pretty it. I hope I didn't talk too much. Voila. Thank you for your attention.
Are there any questions?
Hi, thank you thank you for the talk.
It's an emotional reaction.
Yeah, exactly.
A lot of information.
Thank you for the work, really interesting. I also work on body movement, and I'm extremely interested in the relationship between affect and emotion and movement in general. My question is about the kinematic features, because there's a lot of work that has been done in formalizing the different categories of emotion, but not that much in formalizing what are the actual characteristic of the body that map to that these categories. And so what are the models that you've been using to extract these kinematic features and if you've heard of the Laban movement analysis framework that allowed to do that kind of mapping in a difficult but quite accurate way.
Okay, so I think I understood two questions. So what we have done, and then the consideration of the Laban features.
The Laban, yeah.
Voilà, okay. So I will start from the second one. In this work, we didn't consider the Laban features,
Okay.
but some master students are currently working on it, so it will be done very soon. Now, respect to the first question, what we have done is really address it in a mechanical way, so doing inverse kinematics from joint positions. So you have assumptions on your joints, how many degrees of freedom they have, and you have a stream of positions of your joints, and you try to do what they call inverse kinematics, meaning inferring the state of each bone and the joints. And those are simply raw streams of angles that we acquire in a hierarchical way. So this is, let's say, an implicit way of imposing some structure. Because we impose the hierarchical bone structure of the skeleton. And basically, it's the prediction model, the random forest, that is implicitly handling the relevance.
Oh.
So I would say we have access to this information, which is one of the advantages of more decision trees, because you can explain what happened and why it happened, but we don't look for it after anymore. So we didn't really analyze. So I don't know if I'm answering your question.
Meaning that you're not adding knowledge to how the model is extracted.
It's a
Okay.
purely numerical approach.
Okay.
Voilà.
Well, I'll be happy to talk about it.
Yeah.
So I was wondering, the first data set for the four basic emotions, they were acted out, right?
Yes.
So I was wondering for the second one, where you were looking at predicting valence and activation, were they also acted out, or it was some naturalistic tasks?
It was a naturalistic, you're done with the
Right,
question.
and if it was a naturalistic task, how did you get the labels for arousal and valence? Valence is quite easy to label, but arousal is not that easy. So I was wondering if you could comment on how you collected the labels, the ground truth for the second.
Yes. This is a very good question. Well, we simply, if I can say, organized, and I'm still organizing an annotation campaign. So meaning trained students from the psychology department are continuously annotating all the data we have acquired with the child-robot interaction. And with the annotated data we have, we just test our algorithms on them. We train them on some various data sets, and which the first part of the annotated data set we have acquired in our lab, and then we test them on some unseen, as that was shown there, unseen interaction.
So even for activation, you got good intercoder reliability?
For activation, it's a bit more difficult. This is true. Okay, I will not lie, I show you valence and not activation. So let's be honest here. It's indeed more difficult, but we are working on that.
That's great, so maybe we can follow up later. Thanks.
Okay, the last question, since we are getting into the coffee break
well, it was
now.
two quick questions. One is, it was a very interesting talk, by the way, James Crowley from Grenoble Institute Polytechnique. I don't find a paper in the proceedings. I assume the program's chair can explain that this was an invited talk, there's no paper. Do you have a published paper with these results?
This is a TIIS paper, so there is a paper that has been published during the last year. So it's available in TIIS journal.
Okay, so I'll look that up somewhere else. And my scientific question was, do you think this could be extended to dominance?
So the other, let's say, dimension. Okay, I will adopt more data-driven way of answering the question. But extended, yes, it can be extended, for sure. If you have the data and you have some means to evaluate it, you can do it. There are some indications that perhaps it is possible to infer some information about dominance from the body, but now will it work? This I don't know. Didn't consider it so far. We only work with valence arousal for some other reasons, and
we can discuss it offline. I have a theory also.
Okay, so let us thank our speaker again. And you are all invited to the coffee break. We are 5 minutes late. I apologize for that, but the discussions were very interesting.
All right, this still works. I just wanted to say that the Stone Room's now open for people who are doing posters and demos. If you want to set up, you don't have to do it now, but you're welcome to do so. Student volunteers have maps and stuff. Stone Room, if you walk out the front of the lobby, it's on your right. It's the building made of stone. Probably you can find it that way.